So in magnetostatics we have two important laws. One is the Biot-Savart's law and the other is the Ampere's law. Okay. So first we will deal with the Biot-Savart's law. So consider a current carrying conductor, right? So when there is a current is associated with a moving charge, right? What is I? It is given as the rate of flow of charge, right? So moving charge will constitute current. So a current will give rise to a magnetic field. Okay, so if I is a constant value, right, that means the charge is moving at a constant velocity, and so a magnetostatic field is going to be produced. Okay, so now according to the Biot-Savart's law, if you take a differential current element, okay, so let us say the length is dl. Now you want to find out the magnetic field at a point, say P. Okay, so because of this differential current element, what will be the magnetic field? So if this distance is r, okay, and we take it as a vector from the current element towards the point P. Okay, so then the differential magnetic field, right, because it is only because of the differential current element, right, so it is dH. So dH is equal to, it is a vector, okay, I dl bar cross AR bar. AR bar is nothing but the direction, this direction, right, a unit vector in this direction. I dl bar cross AR bar divided by 4 pi r square, or you can write AR bar, you can write as, from this you can write, right, r bar by mod r you can write. So this you can also write as I dl bar cross r bar divided by 4 pi r cube. Okay, so this is called as the Biot-Savart's law. Now one important thing that you need to know here is what is the direction of dH bar. So once you know how to get the direction of the cross product, then you can get the direction of dH bar. Okay, so if you draw these two vectors, see what is I dl bar, this is dl, I dl bar is going to be in this direction. Okay, and what about r bar? R bar is in this direction, right? So if you draw these two vectors again, this is I dl bar and this is r bar. Okay, so how will you now get the direction? So this diagram here, it will help us understand, right? So here if you can see, there are two vectors here, one is a bar and one is b bar. Now we want to find out the direction of a vector c bar, which is the cross product of these two vectors. Okay, so whichever vector is first, at that vector you have to keep your four fingers stretched. This is the right hand. Okay, this is the right hand. Okay, so now from this you keep your four fingers stretched in this direction and you wind them towards the second vector. Okay, so that is what the fingers have been wound in this direction from A to B. Okay, so when this is done, then what is the direction of the thumb? This is in the upward direction. So that is how you got the direction of vector c bar. Okay, similarly here you have I dl bar cross r bar. So now you have to put your four fingers along, say this is the top view of your four fingers. Okay, now from here you have to wind in this direction, your right hand you have to wind in this direction. Then what will be the direction that you are going to get? The thumb is going to be into the plane. Thumb direction is into the plane. Okay, so from here you can get that the magnetic field at this point P. Okay, what will be the direction of magnetic field here? It is going to be into the plane. So we will now see what is the magnetic field, what is the shape of the magnetic field because of a current carrying conductor. Okay, so if this is a current carrying conductor, let's say on the plane of the paper, right? Now if you take a point P here, okay, just like in the previous case, we will get the direction will be inside into the plane, okay. And similarly, if you take the direction all around the current conductor, then you're going to see that the magnetic field is going to be something like this, okay, concentric circles, okay, and this is the direction H bar, okay. This is the magnetic field. Now one thing that it will often come in helpful is if you have a current carrying conductor, we should be able to decide what is the direction of the current, okay. So for that we make use of the right hand rule again. So this is how you can understand. There's a current carrying conductor here. So in the direction of current flow, if your thumb is present, so you have to hold the current carrying conductor with your right hand, okay. Remember, it's the right hand, okay. So you hold the current carrying wire in such a way that the thumb is in the direction of the current. So the direction in which the other four fingers are going to wind around the conductor, that is the direction of the magnetic field, okay. Now we will see what is the magnetic field due to a finite current carrying conductor, okay. Finite means nothing but it has a finite length. So we will consider there is a conductor here. Let us say the length is L. So this length here, okay, so that is L. Now we want to find out the magnetic field due to this conductor at, say, point P. This is the point P, okay. So what do we do? First you can construct, can just join these two ends to the point P, okay. So now let us say this angle is alpha 1 and this angle is alpha 2, and if you draw a perpendicular onto this line from P, this is a perpendicular line, then this is the distance R, okay. So if these are the dimensions, then you're going to get the H bar. This is going to be I by 4 pi R cos alpha 2 minus cos alpha 1. And what is the direction here? See, direction, it will depend on the current direction. So if the current direction is upwards, okay, then you can take the tangential direction, which will be A phi bar, okay. But if current direction is, say, downwards, then what will be the direction at this magnetic field at this point? It is going to be in the, if you see from the upward direction, then it is going to be in the clockwise sense. So it is going to be minus A phi in that sense, okay. So here you can write the direction is A phi bar or minus A phi bar depending on the current direction, depending on direction of current. So this direction of magnetic field you have to find out from the right hand rule. Next is the Ampere's circuital law. So in short we call it as Ampere's law. So this law states that the line integral of H bar, what is H bar? It is the magnetic field intensity, okay. So line integral of H bar around a closed path, okay. So this point is important. Around a closed path is same as the net current enclosed by the path, same as the net current enclosed by the path. So the integral H bar dot dl bar, the closed line integral, right? Whenever you put a circle here on the integral, it means it is the integral around a closed path. This is equal to the enclosed current. So this is the mathematical expression. Now using the Stokes theorem, we can convert a line integral to a surface integral, right? So here the closed line integral h bar dot dl bar, this is the line integral, this can be converted to surface integral as del cross h bar. What is this? It is the curl of h bar dot ds bar. Okay. So the left hand side of the Ampere's equation we can write as del cross h bar dot ds bar integral, surface integral. Okay. And also, what about this is the LHS? Then what about the RHS? The current we can express in terms of the current density. Okay. So if you express in terms of current density, we are going to get in terms of surface integral. Okay. So integral surface j bar dot ds bar. Okay. So now if you equate, see what will be the equation here? The surface integral del cross h bar dot ds bar, this is the left hand side. The right hand side also we will express in terms of the current density. So since both are surface integrals, we can equate the functions here. What are the functions? Del cross h bar will be equal to j bar. Okay. So this is another way in which the Ampere's circuit law can be expressed. Del cross h bar is equal to j bar. So this is called as the Maxwell's third equation. So we will learn about the complete Maxwell's equation later, but for now you need to know this is one of the Maxwell's equation or third Maxwell's equation. Okay. So if you observe one thing here in electrostatics, we saw that what was the del cross E bar in electrostatics? Del cross E bar, it was 0, right? So this means that the electric field is a conservative vector. Okay. But here del cross h bar is equal to j bar, it's not equal to 0. Okay. So this means that the magnetostatic field is not conservative. Okay. Magnetostatic field is not conservative. Okay. So this point is important. Electrostatic field is conservative, but magnetostatic field is not conservative.